I had previously uploaded this to YouTube, but it appears that there was some sort of glitch, so we'll redo it. What we want to start thinking about is how we can integrate rational functions, which is a fraction of two polynomials. Before we get started, I think it might be enlightening to kind of reverse engineer what's going on here. So suppose I had three rational functions, but they were a very simple variety. They are linear polynomials on the bottom and constants on top. If I want to add these fractions together, I have to fix it so that the denominators are all the same. The lowest common denominator is obviously going to be x plus 1 times x plus 4 times x minus 1. So in each one of these fractions, I've already got one of those three things on the bottom, and I just have to supply the other two. So in this first one, I'll put a factor of x plus 4 in the top and bottom, which naturally doesn't change anything. Also, I'll put a factor of x minus 1 in the top and bottom. In the middle, I've already got the x plus 4. What I don't have is the x plus 1, so I'll put it in the top and bottom, and the x minus 1. In the last chunk, I've already got the x minus 1, so I just have to put in the x plus 1 and the x plus 4. If I add together three things like this, on the bottom of the fraction, I'm going to have a third-degree polynomial, a cubic, while on top, altogether, I'll have a quadratic or lower degree, depending on the details. In many cases, the reverse is true. If I have some quadratic divided by a product of three linear factors, x minus alpha, x minus beta, x minus gamma, if the alpha, beta, and gamma are all different from each other, there are no repetitions, then it turns out that it's always possible to take something like this and write it as a sum like that. Now, this is actually very useful. If I wanted to integrate x minus 1 over x cubed minus 5x squared plus 6x, I'd look at that and I'd think it's a higher degree polynomial on the bottom, lower degree on top, and if you look at what's on the bottom, obviously you can factor an x out of everything, and x squared minus 5x plus 6 factors up nicely. The bottom of the fraction is x, which is to say x minus 0, times x minus 3 times x minus 2. The bottom of that fraction factors up into three distinct linear factors, and according to the reverse engineering idea, we ought to be able to do something with that. Now, there's a bit of philosophical trickery going on here. I'm going to look at my function, the rational function. I want to think of it as a over x plus b over x minus 3 plus c over x minus 2. I want this to be true every place where the formulas make sense, but obviously if x were 0, this wouldn't make sense. If x were 3, it wouldn't make sense. And if x was 2, I'd get division by 0, which doesn't make any sense. We're going to proceed on the tacit assumption that x is not 0, 2, or 3. If so, I can multiply through by this bottom. When I cancel out common factors, I find out that x minus 1 needs to be a times x minus 3 times x minus 2, because the x's canceled out, but the other two factors didn't, plus b times x minus 2, the x minus 3 factor canceled out, plus c times x minus 3, the x minus 2 cancels out. Now, we just explicitly said a minute ago that I should never stick x equals 0 or 2 or 3 into this thing. So naturally, that's what we're going to do. We need to talk about that a little bit. If I stick x equals 0 into this formula, the left-hand side is 0 minus 1. Put x equal to 0 in all of the expressions. The only term that isn't 0 is the one with the a in it. This tells me that -1 and 6 times a are the same thing. That is to say, a is -1/6. If you take x equal 2 and put it into this formula, 2 minus 1 is 1. If x is 2, this term is 0 because of the 2 minus 2. This term is 0 because of the 2 minus 2. And all you have left is c times 2 times -1. This tells me that 1 is -2 times c. c is -1/2. And by putting x equal 3 into this formula, which I think your textbook calls the basic equation or the auxiliary equation or something like that, you eventually find out that b is 2/3. Now, I do have to say at least a word about what we're doing, because on the face of it, we are doing exactly this thing that we said we shouldn't do, but it's okay. This equation is true for all x's except x equals 0, x equals 2, and x equals 3. That means that this equation is also true for all x's except 0, 2, and 3. On the other hand, this is a polynomial. This is a polynomial also. Polynomials are nice continuous functions. If you want to take the limit of a polynomial as x approaches c, it's the same thing as just plugging x equals c in. That's why this is working. I'm not really plugging x equals 0 into this. I'm thinking, I'm going to evaluate this at some place that's close to 0, and then I'm going to take the limit as x approaches 0. Because these are polynomials, this side would simplify down to 0 minus 1. This would simplify to a times -3 times -2. This would simplify to b times 0 times -2. And this would become, in the limit, c times 0 times -3. On one level, I shouldn't be sticking x equals 0 into this. What I'm really philosophically doing is taking the limit as x approaches 0. But since these are really nice functions, it has the same effect as if I had set x equal to 0. The same comment applies to x equal 2 and x equals 3. So really, everything's fine. It just looks like we're doing something illegal here. As a comment, the integral 1 over x minus a constant with respect to x is very easy to do. You make a u substitution. You figure out what du is. The integral turns into integral of 1 over u du, which is natural log absolute value of u, plus a constant, if that were all there were to it, which is natural log absolute x minus a. So if I have an integral that looks like this, I'm very happy to see that. That's an easy integral to do. Why were we doing this again? We're writing the integrand, the thing that I want to integrate, as a sum of simpler, easier to deal with things. This is the integrand, and it worked out to be this. We're going to call this the partial fraction expansion for the thing we're trying to integrate. Since this is that, the integral of this with respect to x is the integral of that with respect to x. And if you look at it, everything that's left is easy to integrate. -1/6 times an antiderivative 1 over x. -1/6 natural log absolute value of x. plus 2/3 times an antiderivative of 1 over x minus 3, 2/3 natural log absolute x minus 3, minus 1/2 times an antiderivative of 1 over x minus 2, which is what you think it is. And now that we have one antiderivative, add a constant of integration to get all of them. If you wish, you can leave it like that, or you could use properties of logarithms to try to combine things. In my view, it doesn't make any difference. What we've got at the bottom of the previous page is a perfectly legitimate answer. If you want to use the laws of logarithms from algebra, you can do that and write your result in this form if you think it looks nicer. Now, in our long division, we saw that if I add 3 of these nice 1 over x minus a constant functions, I get a cubic on the bottom and a quadratic at worst on top, lower degree on top, higher degree on the bottom. What if that's not so? What if you want to do the integral of a rational fraction and the degree of the top is equal to or even bigger than the degree of the bottom? This turns out by itself not to be a problem. We will fix this with long division. So I want to integrate the following function, x cubed plus 2x squared plus 5x plus 1 divided by x squared minus 1. I'm going to use long division to produce the divisor, the remainder, and the dividend. X cubed plus 2x squared plus 5x plus 1. The thing I'm dividing by, x squared minus 1, doesn't have an x to the 0 power, an x to the 1 power term in it. So I'll keep my bookkeeping straight by putting in 0 times x for that. This begins with x cubed. That begins with x squared. I need to multiply this by something that starts off with x in order to get that x cubed. So my first thing is going to be x. X times x squared is x cubed. X times 0x is 0x squared minus 1 times x. Put parentheses around that and subtract away, just like you would do if these were digits in an actual number problem. 2x cubed minus, x cubed minus x cubed is 0. 2x squared minus 0x squared is 2x squared. 5x minus negative x is 6x, and then you bring down the next term. If this was actual long division, you would be bringing down the next digit. I'm now working with this thing 2x squared plus 6x plus 1. I need to multiply this by something so that the result starts off with 2 times x squared. Obviously, I'll need a 2. 2 times x squared is 2 times x squared. 2 times 0x is 0x. 2 times minus 1 is minus 1. Put parentheses on it and subtract. The quotient works out to be 2 plus x, and there's a remainder. The remainder is 6x plus 3. So the fraction that we're trying to integrate works out to be the quotient plus the remainder divided by the divisor. When I want to integrate the thing that I started with, it's the same as integrating x plus 2 plus 6x plus 3 over x squared minus 1. This part is easy. It's a polynomial, so I'll just go on and write it down. 1/2 x squared plus 2 times x. In what remains, I've got a quadratic on the bottom and a first degree polynomial on top. So if I can factor this denominator, then I can go back and do my partial fraction thing again. We'll figure this out, and we have to remember to include this part as well. But x squared minus 1 is x plus 1 times x minus 1. I'm going to multiply through by x plus 1 and by x minus 1. And after you cancel terms that will cancel out, you get the characteristic equation or the auxiliary equation or whatever your book calls it. Again, strictly speaking, this is only true if x is not 1 and x is not -1. But as we said before, because these are polynomials, I may as well just think of taking the limit as plugging the inappropriate numbers in. If you put x equal -1 into this, 6 times -1 plus 3 is -3. -1 minus 1 is -2. -1 plus 1 is 0. So the part with the b in it goes away. This has to be true. So that tells me that a is 3/2. The other number that I shouldn't mess with is x equals 1. Put that into this equation. 6 times 1 plus 3 is 9. If x is 1, this chunk is going to be a multiplied by 1 minus 1. So that's going to be a times 0. This piece is going to be b multiplied by 1 plus 1. That would be 2b. So we find out that 9 has to be 2 times b. b has to be 9/2. So we know the a into the b in this partial fraction expansion. Again, the reason that we're doing this is so that we can take that last part in the problem that we didn't know how to deal with and write it as something nice. The two integrals that you've got are of the nice variety. So I'm going to have integral 6x plus 3 over x squared minus 1 is 3/2 times natural log absolute x plus 1 plus 9/2 natural log absolute x minus 1. So putting all the pieces that we've figured out together, the integral that is, we're not doing derivatives, the integral is 1/2 x squared plus 2x plus 3/2 natural log absolute x plus 1 plus 9/2 natural log absolute x minus 1 plus a constant. If we felt like it, we could combine those last two terms into one using properties of logarithms, but I'm just going to leave it like that. So we're getting somewhere now. We can integrate anything that looks like the integral of p of x over q of x with respect to x, where p and q are polynomials, if the polynomial on the bottom can be factored into distinct linear factors. If it's like that, we know what to do now. There's two things that could go wrong here. One of them is something like 3x plus 1 over x cubed minus 2x squared plus x. If you look at the denominator, you can factor an x out. What's left is x squared minus 2x plus 1. And you remember from algebra that that's the square of the quantity x minus 1. The bottom of the fraction is a cubic polynomial, but it doesn't split up into three distinct linear factors. I've got an x, I've got an x minus 1, and then I've got another x minus 1. If this happens, it's not too difficult to fix it. But it should be clear that 3x plus 1 over x times x minus 1 times x minus 1, that can't be a over x plus b over x minus 1, because that's what you would get if you were doing the expansion of 3x plus 1 over x times just one factor of x minus 1. If you do some more reverse engineering, it turns out that the thing to do is this. If I have a linear factor on the bottom that is distinct from all the other ones, different from all the other ones, then you just write down what you would think you would do. If I have a linear factor that is repeated, I'm going to have several terms involving that factor, and each one of them is going to look like a constant divided by a power of the linear factor that gets repeated. Here, x minus 1 occurs twice, so what I'll have is b over x minus 1 plus c over x minus 1 squared. If this had been x minus 1 cubed, I would have plus d over x minus 1 cubed, and so on and so forth. Once again, I should never plug x equal 1 or x equals 0 into this, but by now we understand that that's exactly what we should do, but only after we've gotten rid of the fractions. So multiply through by x times x minus 1 squared. Over here, all that's left is the top of the fraction. In this chunk, the x cancels out, but the x minus 1 squared didn't. In this one, the x doesn't cancel out. There's no x on the bottom. I'm multiplying through by x minus 1 squared. One of those cancels out, but you still have the other one. Plus, when I multiply this last fraction by x times x minus 1 squared, x will remain, and x minus 1 squared cancels out. So this equation that we're going to use now reads like this. There's good news and there's bad news. The good news is I have two special x numbers which I can put into this equation and maybe figure something out. What if x was 0? 3 times 0 plus 1 is 1. Negative 1 squared is 1. 1 times a. If x is 0, this term is 0, and so is that one. So this immediately tells me that a has to be 1. What if x was 1? On this side of the equation, I'm going to have 3 times 1 plus 1, which is 4. If x is 1, then this chunk is 0, that chunk is 0, and that chunk is c times 1. So that immediately tells me that the c has to be 4. This has been the good news. And then there's the bad news. I have no more special numbers to put into that formula that make terms go away. At first glance, it seems like we're kind of stuck, but there's a way out of this. This formula is supposed to be true for all x's. Now, I'm not going to get any more mileage out of x equals 0 or x equal to 1, but this is supposed to be true for any x. So what I'm going to do is I'm just going to randomly pick some x number that's not one of the two special ones. I'll pick x equal to 2. 3 times 2 plus 1 is 7. 2 minus 1 is 1 squared, which is 1. If x is 2, this is b times 2 times 1. That would be 2b. And if x is 2, 4 times x is 8. And see, this is an equation that only has one unknown thing in it. So do all the algebra, and it turns out that b is negative 1. So the integral that I want to do is actually the integral of 1 over x minus 1 plus 4 divided by x minus 1 squared with respect to x. These first two are the nice kind, the ones that I can just look at and tell you what the antiderivative is. The last one, I can factor a 4 out, and I can do this last integral with a u substitution. Make u equal x minus 1. Work through the details of that. It turns out that the integral of 1 over x minus 1 squared is negative 1 over x minus 1, and then put the 4 back, and you have the integral of that last term. So now we're at the point or the integral of a polynomial divided by another polynomial with respect to x, we can integrate that as long as I can split the cube, the thing on the bottom, up into linear factors. There's one other thing that can go wrong with this. It's possible that you could have a quadratic factor that doesn't have any real roots. What that means is there's no way to write that as x minus a real number times x minus another real number, because if you could, it would have two real roots. So for example, x cubed plus x is x times x squared plus 1. X is a nice linear factor, so we would be happy to see that, but x squared plus 1 can't be split up into linear factors in the real numbers. If you were willing to work with complex numbers, though, you could do it. It would be x plus I times x minus I. Unfortunately, doing calculus with complex numbers turns out to be extremely complicated, and we can't go there at this current time. If it had been x cubed minus x, that would be okay. That's x times x squared minus 1, which is x times x plus 1 times x minus 1, and these linear factors are all distinct. X cubed plus 2x squared plus 2x, x multiplied by x squared plus 2x plus 2. If you check, that second quadratic factor doesn't have any real zeros, so there's no way for me to split it up into a product of linear, real, first degree, nice looking polynomials. That can't be done. Usually, when we say that you can factor a polynomial, we've got kind of a snobbery about it. We only want to see nice whole numbers for the coefficients, maybe even some fractions, but that's about it. X squared minus 7 can be split up in the real numbers. It's x plus radical 7 times x minus radical 7. If you multiply those two things out using the FOIL method, you'll find out that it's x squared minus 7. So even though I don't have something nice here, like a 4 or a 9 or a 16, that's perfectly fine. Linear factor, different linear factor. On the other hand, x squared plus 7, there's nothing you can do with that in the real numbers. So in a situation where I can factor something, but it's not factoring in the usual sense of the word, people wouldn't like radical 7 for a coefficient. If it's impossible to split something up, we say that it is irreducible. If it is possible to split it up, we call something like x squared minus 7 reducible. Reducible is just a fancy way of saying you can factor it, but the factors are not going to look as nice as they usually do. So if I want to calculate the integral of x over x squared minus 4 times x squared plus 4, you look at that x squared plus 4 and get kind of a sinking feeling in your stomach because you can't split it up into real linear factors. On the other hand, I am happy to see the x squared minus 4 because that's x plus 2 times x minus 2. We will write this. The general strategy is the same as before. Here I've got a linear factor and a constant polynomial. Linear, constant, quadratic, linear. If you multiply through by the bottom of the fraction, it turns into the usual sort of thing, except it's a lot messier looking than usual. There are some numbers that I should never stick into this thing. I should never stick x equal 2 into it because that would give me division by 0. So stick x equal 2 into that and grind through all the details. The only chunk that isn't 0 on the right turns out to be 32 times b. So b works out to be 2 over 32, which is 1/16. We now know that number. So I'm going to write my equation down again, but since I actually know what b is already, I'll go on and write that in. I'm also supposed to never stick x equal -2 into that equation, so go ahead and do that. When the dust finally settles, you find out that a is 1 over 16 as well. So since I now know a and b, I'll write those in. I have two numbers that I have to figure out, and then I will know my partial fraction expansion. I need to figure out the values of c and the values of d, but I'm out of luck as far as special numbers go. One idea is this: pick two other numbers. Don't pick them to be -2 or 2, though, because that's not going to tell you anything. And put them into this formula. You'll get two equations, both of which involve c and d. And if there's any luck in the world, maybe you can solve that pair of equations for c and d, and then figure out the partial fraction expansion. Idea number 2 is to take this equation and actually multiply everything out and compare the quadratic coefficient on this side to the quadratic coefficient on this side, which is 0, the x to the first power coefficient to the x to the first power coefficient, which is 1. Figure all this stuff out, look at its constant coefficient. The constant coefficient of this is 0, so that would give you another equation. I'm going to try two other numbers. I'm going to try the first one. I just made this up out of thin air, and it turns out that a miracle happens. Try x equals 0. If x equals 0, you get 0, 1 over 16 times -2 times 4, plus 1 over 16 times 2 times 4, plus c times 0 plus d times 0 minus 4. Luck is with us. This is 0, so the c disappears from the equation. After you get done multiplying and simplifying, you find out that 0 is -4 times d, which says that d is 0. This is just luck. If I picked some other number, probably this equation would reduce down into something that had both c and d in it, and I would have more work to do. So put in the fact that d is 0, my equation now turns into this. And finally, I'll pick x equal to 3, put it into the equation, grind through the arithmetic, and when the dust finally settles, c works out to be -1/8, if I've done all of my arithmetic correctly. Putting the results back into my integral, this is easy to integrate. That's easy to integrate. We're going to have to think about this one. For this one, 1 over 16 times natural log absolute x plus 2. For this one, 1 over 16 absolute value natural log x minus 2 minus 1/8. I'll pull that out in front of the integral. I've got to figure out how to do that. And I believe I see an error here. If you let u equal to x squared plus 4, then du is going to be 2x dx. The derivative of x squared plus 4 is 2x dx. So this integral is actually natural log absolute x squared plus 4, but I had including this extra factor of a half, so I'd made an error there. Other than that, you could leave this as is, or you could use properties of logarithms to combine. I'm just going to leave it like that. So what do we like? We like distinct linear factors. If we have repeated linear factors, we like that slightly less, but it's not very complicated. If we have an irreducible quadratic factor, we're not happy about that at all. And of course, the worst thing that could happen to you would be to have an irreducible quadratic factor that's repeated. Now, you shouldn't take this too seriously because the amount of work needed to do these integrals becomes monstrous in a situation like this. It's enough to know what you would do if you were actually going to do it. So if you want to look at the integral of 1 over x minus 2 times x minus 4 to the third power times x squared plus 2x plus 3 times x squared plus 1 squared, the only thing I really like a lot about this is the x minus 2. The fact that I've got a repeated x minus 4, I've got 3 repetitions of it altogether, makes me less happy. We begin with a over x minus 2, b over x minus 4, c over x minus 4 squared, d over x minus 4 cubed. This x squared plus 2x plus 3 has no real roots, which means you can't split it up into real linear factors. You would have to have x squared plus 2x plus 3 on the bottom and a linear factor on top, ex plus f. X squared plus 1 doesn't have any real roots, so x squared plus 1 is a quadratic irreducible factor. But worse than that, I've got 2 of them. So you would have x squared plus 1 on the bottom and x squared plus 1 squared on the other one. Upstairs, linear factor gx plus h. Upstairs, linear factor ix plus j. So if you actually wanted to do this, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 unknown coefficients to find, and it's just going to be an algebraic nightmare to do this. So if ever I give you something on the take-home test that even vaguely involves something like this, it's going to be this. If you wanted to do this integral, what is the form of the partial fraction expansion that you would have to do? And this would be your answer. I'm not going to ask you to actually do something like that. It's not reasonable. Anyway, as I said, I had uploaded this before, but I looked and apparently it got lost somewhere. So here's partial fraction expansion. We also want to talk about L'Hopital's rule and also improper integrals. We'll be getting to that soon. In the meantime, I hope everyone is doing well. I'll talk to you again soon.